Hello, everyone. This is Ahmed Mahmoud from DataMind AI. Welcome back. Today, we are diving deep into Databricks Lakeflow, the evolution of declarative pipeline and engineering at scale. This is the 2026 edition, which means we will be covering the latest features and the best practices that are transforming how we build the data pipeline. And today, we are going to focus on schema evolution in Databricks. This is the pain that every data engineer has experienced. You build a stable pipeline and everything works. Then one day, boom, production is down. And why? Because someone upstream added a column or changed the data type or renamed the field. So let me walk you through each scenario. New column added. Traditional pipelines have fixed schema. When a new column appears, the reader either fails because it was not expecting it, or it silently drops the column because it is not in the expected schema. Either way, you lose the data. Now, what about column dropped? Even worse, if a downstream transformation or expectation references that column, the entire job crashes, and you might not find out until production breaks. Now, data type changed. This is particularly nasty. String to integer, for example, might work sometimes and fails other times. Int to decimal can cause precision issues. The pipeline either crashes or produces nulls, and tracking down why is a nightmare. Now, column renamed. This creates semantic chaos. Is customer ID the same as cust_ID? Your joins breaks, your expectations fail, and therefore you might end up with duplicates if the old and new columns both exist. Now, the fundamental problem is traditional ingestion treats schema as fixed. But in real world, schemas evolve. That is where schema evolution comes in. Let me give you the clean definition. So schema evolution is the ability of a pipeline or a table to adapt safely when the incoming schema changes, while still enforcing required fields and data quality rules. Read that again, safely and while enforcing rules. This is the key distinction. So safely and while enforcing rules. Schema evolution is not anything goes. It is not disable all checks and hope for the best. It is controlled flexibility. Think of it like this. We allow change, but we control it. You can add new column, fine. We will handle that. You cannot drop a critical field though. We will fail and alert you. You can evolve the schema, but you cannot violate the contract. This is what makes schema evolution production ready. You get adaptability without chaos. It's the difference between a brittle pipeline that breaks on every upstream change, a resilient pipeline that adapts while maintaining quality. So let us look at the specific problem this solves. Here are the 5 critical problems that schema evolution solves. Number 1 is the migration support. So when you are migrating from a V1 source to a V2 source, you often need to run them in parallel during the transition. Now, schema evolution lets you union both sources into one table, even though they have different schemas. This is huge for zero downtime migration. Now, number 2 is like additive change. So the most common change, schema change is adding a new column. So with the schema evolution, you can add columns to the source without breaking every downstream consumer. So the new column just shows up as nulls or for historical records. Yeah, clean, simple, safe. Now, backwards compatibility. Here's the scenario. You have, for example, 6 months of historical data with the old schema and new data coming in with an updated schema. So without evolution, you would need to reprocess all historical data or maintain two separate tables. So, but with evolution, old records load just fine. Missing columns are filled with nulls. Now, number 4 is pipeline resilience. This is about operational excellence. With the schema evolution, your pipeline do not break every time an upstream teams makes a change. Less downtime, less emergency fixes at 3 a.m., for example, less firefighting. Number 5 is enforced contract, and this is the magic. You still enforce your data contract. You can say these fields are required, these type are mandatory, this value must pass validation, even while allowing the schema to evolve. It is governance flexibility. Now let us talk about which file format actually support this. Not all file formats are created equal when it comes to schema evolution. So let me break this down. CSV, this is low evolution friendly. CSV does not store schema at all. Column orders also matter, so type inference is a nightmare. If you add a column, you have to hope it is at the end and everyone remembers to update their reader. So if you reorder columns, everything breaks. This is why CSV are terrible for production data pipeline. So they are fine for quick export, but not for governed data platform. Now you have the JSON one. So it is medium evolution friendly. So JSON is semi-structured, which gives you flexibility. You can add fields, remove fields, nest structure, but flexibility is also chaos. Nested changes are particularly messy. So if someone changes the structure of a nested object, your downstream code breaks and there is no schema enforcement. So you are relying on documentation and hope. Now the Parquet file, it is medium to high evolution friendly. Parquet stores the schema in the file metadata. This is good. You can add columns and readers can handle it, but Parquet does not have ACID properties or a transaction log. So governance is harder. You cannot easily track schema change over time, and handling schema conflicts requires manual intervention. Now you have the Delta Lake, the gold, high evolution friendly. Delta is the winner here. It stores schema in the transaction log. So every schema change is versioned and tracked. You get ACID properties, so you can enforce the schema on write. You can evolve schema safely with built-in commands, and you have full history. You can always see what the schema was at any point in time. Here are the most important points. CSV and JSON are flexible, but not governed. Yeah. Delta is governed flexibility. You want governance, you want auditability, you want schema evolution with quality enforcement. That is why we use Delta for production data platforms. Now, let us talk about the specific pattern for schema evolution in DLT. Now, when to use this pattern, you have a legacy source V1 and a new source V2. Maybe you are migrating from an old system to a new one. Maybe your upstream team redesigned their schema. Either way, you need to handle both. So you want one unified table or view, not two separate tables, not complex switching logic, one clean unified dataset. So, and also you want backwards compatibility. Historical data with old schema needs to keep working. So new data with new schema needs to to work too. So you want quality enforcement? This is critical even while the schema evolves. You still enforce your data contract. Required fields stay required, types stay enforced. So expectation is still run. So the key technique is to allow missing column is equal to true. Yeah. So if you add allow missing column equal to true, the magic happens with this one parameter in a union by name. Here's what it does. Normal union by name requires exact schema match. Yeah. If source A has column X, Y, and source B has X, yeah, and Y, Z, the union fails. With allow missing column though true, the union succeeds. It fills missing columns with null. So if V1 source has student ID, name, GPA, and V2 source has student ID, name, GPA, and email, V1 records get nulls for the email column. V2 records have all the columns filled. So you get one unified data set. This is a schema evolution in action. So let me show you the actual code. Now, here is the actual code for schema evolution in DLT. Let me walk you through this step by step. The first line is imports. We are using Delta Live Tables pipeline as DP, and we need some Spark function as well. So the decorator is we define a table called student underscore unified. Notice we are still using expect underscore all underscore or underscore drop. So schema evolution does not mean we drop quality enforcement. We are still requiring student ID to be present and GPA to be valid. This is governed evolution. Now, V1, which is the source, yeah, the legacy source has 3 columns, student ID, name, and GPA, for example. So we add a source version column so we can track which version each record came from. This is useful for debugging and auditing. Now, version 2 source, this new source has 5 columns: student ID, name, GPA, email, and phone. 2 new columns have been added here. We also tag it with source version 2. Now, the union, this is the key line here. This is very important. V1 dot union by name, open bracket V2, comma, and then allow missing columns equal to true, close bracket. Now, without the allow missing columns, this would fail because V1 does not have email or phone. With the allow missing columns is equal to true, it works. V records gets null for email and phone. V2 records have all fields populated. So the result is you get one unified table with all 5 columns. Historical V1 records loaded fine with nulls for the new columns. New V2 records have everything, and your quality rules still enforced. Student ID is required, GPA is validated. This is production-ready schema evolution, clean, safe, and governed. Now, let us look at what actually happens to the data. Now, let me show you visually what is happening with allow missing columns. Now, V1 source, which is legacy, 3 columns, student ID, name, and GPA. 2 records like Alice with 3.8 GPA, Bob with 3.2 GPA. This is your historical data. And then you have V2 source, which is new. It has 5 columns: student ID, name, GPA, email, and phone. 1 record, Carol with 3.9 GPA, email, and phone. So this is your new data with the evolved schema. Now the union, which is union by with allow missing columns is equal to true. Without this parameter, the union would fail because the schema don't match. With the parameter, it succeeds. So the result, a unified table, all 5 columns from V2 plus source version for tracking. And notice what happened. Alice and Bob, the V1 records, have null for email and phone. Carol, which is V2 record, has all fields populated. So everyone has the student ID, name, and GPA. This is clean, this is safe, this is governed. So you are not losing data, you are not breaking historical records, you are not dropping quality enforcement. You are evolving the schema while maintaining data integrity. And here is the beautiful part. Downstream consumers can query this unified table. They don't need to know about V1 or V2. They just see one table with all the columns. If they care about email, they filter by not null. If they don't care, they can ignore it. Now, before we close, let me give you 5 best practices for schema evolution. Number 1 is always track source version. So add the source version or schema version column. This lets you know which schema version each record came from. So when we are debugging issues or analyzing data quality, this is invaluable. You can say all the null emails are from version 1 source, for example, instead of guessing. Number 2 is keep quality enforcement. So this is critical. Schema evolution does not mean anything goes. You still use at expected all or drop or at expected all for your required field. So student ID is still required. GPA still needs to be in valid range. Don't sacrifice quality or flexibility. You can have both. And then number 3 is document schema change. So use delta table history, use table comments, document why is the schema evolved. Yeah. So for example, why the schema evolved? Because we added email and phone fields for version 2 student system migration, ticket, project number, whatever, yeah, whatever the project name. So 6 months from now, someone will thank you. That someone might be you. So for test number 4 is test with both schemas. Don't just test with new data, test with old schema data too. Make sure your pipeline handles both. Make sure your expectations still work. Make sure the union succeeds. Test before you deploy to production. Number 5, handle nulls explicitly. So downstream consumers need to know that evolved columns might be null for historical records. Yeah? So if someone writes select email from student unified and expects no nulls, they are in for surprise. Document it, add data quality checks, be explicit about what nulls mean. And these practices turn schema evolution from risky to routine. So let me wrap up with the key takeaways. Now, here are like our takeaways from today's session. Schema changes are inevitable. So upstream system evolve, requirements change, data source get redesigned. You cannot prevent this. The question is, does your pipeline breaks or adapt? So traditional pipeline breaks. So every schema change is a production incident, emergency fixes, manual intervention, downtime. Modern pipeline adapt. So with delta plus DLT, allow missing columns, you get governed flexibility. You can add columns, evolve schemas, migrate sources, but you still enforce your data contract. Required fields stay required, quality rules stay enforced. So evolution without chaos, schema change, don't break production, new columns show up as nulls for historical data, unions work seamlessly, and downstream consumers keep working. So quality without brittleness. You don't sacrifice quality for flexibility. You have both. Validation still runs, expectations still enforce, but the pipeline does not break when schema evolve. This is what separates a mature data platform from professional one. If you're building production data pipeline, you need the schema evolution. It is not optional. It is fundamental. And now you know how to implement it in Databricks with Delta Live tables. So if you got value from this video, subscribe for more deep dive on Databricks, data engineering, and AI readiness. Thank you for watching. Now go build a resilient pipeline.